All right, so in this chapter, we'll now study rotations, okay? So we'll study fixed axis rotation. Yep. So I got to record this thing for an online class, so I will show you a demo, but let me do a drawing first. Okay, so let's say here's a disc or a wheel, and we are going to spin this wheel. Okay, so the wheel is going to rotate. And what the title says fixed axis rotation. What that means is, so the wheel is going to rotate and this axis is going to be fixed. Okay, we are not going to let the axis wobble like that. That is too complicated a motion right now. Okay, so the axis will be fixed, and the wheel will spin about this fixed axis. Let me. Okay. So there's the axis of rotation, and the wheel is going to rotate about this fixed axis. Okay. Now you will see in a little bit that this motion is very similar to motion in one dimension. Okay. So if an object moves in one dimension, okay, so if we restrict it into moving in one dimension along a straight line, okay, so the object can move in that direction, then move back and go back and forth. Okay, its velocity can either point to the right or point to the left. Okay. What did we do for velocities pointing to the right? If that was the positive direction, this was plus 5 meters per second, and this was minus 3 meters per second. Okay, so the direction of the velocity was given by the sign. Okay. And if I asked you to describe this motion, what was I asking you? How would you describe that motion?
With the sign.
I'm sorry?
With the sign, the positive and negative.
No. Well, if I wanted you to describe this complete motion,
I'll simply just add up all the vectors.
well, what was a mathematical way of describing a motion?
Can you ask about the displacement of it?
Velocity function of time. Velocity function of time.
Go
The velocity.
position as a function of time. Okay? So when I asked you to describe a motion, I was asking you what was the position of the object as a function of time. Okay? Given this, so this is a complete description. Given this, I could calculate velocity as a function of time, acceleration as a function of time. Okay? All right, so we are going to apply all of that to this motion, except that this motion looks very different. Okay, so let me tell you one difference about this right away. Okay. So in this one-dimensional motion, okay, here was a car that was driving along like that, and then, there was the motion it made. We treated this car as a point particle. How come we could treat that car as a point particle? Why were we able to treat the car as a point particle?
It has a center of mass.
I'm sorry?
Center of mass.
Well, if the car were spinning and going like that, you couldn't treat it as a point particle. It still would have a center of mass. Okay, so you could treat the object, a large object, as a point particle when every point in the object moved with the same velocity, and so on. But here you run into this problem. When this thing is spinning, you guys understand that this guy has to move faster than this guy, right? Because This guy has to cover a bigger circle, and this guy, in the same time, this guy is going on a smaller circle. So this guy's speed is smaller than this guy's speed. So right off the bat, how do you treat it as a point particle? You can't treat it as a point particle. Okay, so when this thing moved, if the front of the car moved 5 meters, the back of the car also moved 5 meters. Is there anything that is the same when this thing spins? You guys understand the question? Okay.
Would it be possible that the answer would be like in a form of exponents?
No. So you first want to find a coordinate that's the same. Do you guys understand that? So here is the coordinate. Okay, so let's say this is the x-axis, and we mark a line on this object, and we measure the position of the object as theta. Okay, and let's say this object turns a little, and it goes from there to there. So that object turned 50 degrees. This point turned 50 degrees. How about this point? How much did that point turn? 50 degrees. Every point turned 50 degrees. Okay. Now you found a coordinate that is the same for everything. Do you guys understand that? Okay. So now let's see. Okay, so what would be, you guys understanding this? We're going to use the same technology for this guy that we developed for this guy. We'll use the same technology for this guy. Even though this looks very different. Okay. Now we've shown you how we can use the same technology for this motion as we used for this guy. Okay, so what I'm going to do is, okay, so again, like I said, I'm recording this, so I can't show you the wheel, but I'll use that in a second. So here's a wheel that is going to spin like that. So now I'm going to do the following. I'm going to spin the wheel like this, back like that, like this. So that's some kind of motion, okay? And how would I describe that motion? How would I describe that motion? Any general motion. I'll give the position as a function of time. Okay? Did you guys understand that? All right, so let me show you that motion. So here's a general motion. Here's a wheel. Okay. I'm going to measure, let's say I'm going to mark this spoke on the wheel, and I'm going to use that to measure the position. So here's the x-axis. Right now, the position of the wheel is 0 degrees. Okay, so here's a motion. And to describe that motion, what I would give you is position as a function of time. Did you guys understand that? Okay, so that's how I'm going to describe this motion. And I can describe any general motion. Okay. All right. What would be the velocity? So this is the angular position. What would be the velocity? So let's say I make up a function. Let me make up a function 4t cubed plus 3t squared plus 5t plus 7. So here is here's a motion that I've described to you. And what we'll do is, just like you had defined linear velocity, we will define angular velocity. This is angular velocity, and angular velocity would be the time rate of change of angular position. Okay? Angular velocity is denoted by omega, okay? And that's d theta by dt. Okay, so what is the angular velocity? What's the derivative?
8t squared plus
I'm sorry?
8t squared plus 9t plus 5.
12t squared.
12t
Plus
9t
6t plus 5. Okay. And what was the derivative of velocity in linear motion? That was acceleration. And so we'll call this angular acceleration. It's denoted by alpha. And that's equal to d omega by dt. and this is equal to 24t plus 6, okay, and so on. Okay, so here is a motion described, okay, and the units we'll use for the angle will be either radians or degrees, and you'll see that in one particular situation you will always want to use radians, okay. So degrees or revolutions, so we'll tend to stick with radians, okay. So here's the angular position of the object, okay, as a function of time. You could calculate the angular velocity, and you can calculate the angular acceleration. Okay. Those are the things we'll be interested in. Okay. So again, we will be interested in the motion of a rigid object. So rigid object rotating about a fixed axis. This is too complicated to describe. Okay, now let me ask you one more thing. Why do we want to do only rigid objects?
To account for friction?
No. Why rigid objects? Because, yeah,
Could mess up the axis of rotation.
no. You want rigid object because remember what this was the position of what point? It can be the position of any point. You want rigid objects because every point rotates through the same angle. Okay. Now you take a cup of coffee and stir the coffee toward the end of the cup, near the cup, is not rotating through the same angle that in the center. Okay. So we want to keep things simple. Okay, again, we're not going to let the axis wobble. That's too complicated. And we're going to stick to rigid objects. Okay, so that's what we're going to describe. Okay. All right, so we're going to talk fixed axis rotation for rigid objects. Okay. All right, you guys can read all of this here. By the way, this is a centrifuge, and this is in Houston. You can put an astronaut there and spin them real fast. You can subject them to 20 Gs and make them pass out. Okay. So we are studying rotating objects, and you see rotating objects all over the place. Okay. When an extended object rotates, all parts of the object do not have the same linear velocities and accelerations. Okay, so hence the motion of the object cannot be analyzed treating it as a point particle. Yes, so, and we had to come up with a new coordinate. However, for a rigid object rotating about a fixed axis, okay, so for instance, for this guy, the axis would be that horizontal axis, that would be fixed, okay? And every point on the blade rotates through the same angle, okay? So that would not be true if, for instance, if that was a liquid in a cup, for instance, okay? So for a rigid object, all parts of the object rotate through the same angle, and we're going to use this to describe its motion. Okay, so here's an object. This will be a reference line, so from which we'll measure the angle. So this can be the x-axis. You have an object. Here's a rigid object. The axis of rotation is perpendicular to the plane, so it's coming out of the sheet. And we'll mark a point on the object, and we'll measure the position of this object with reference to this axis. So right now, the position of this object with reference to this reference line is, let's say, 30 degrees. If it rotates another 60 degrees, its position would be 90 degrees, or pi by 2 radians, okay? So you guys understand that? So you can spin this any which way you want, and to describe that motion, what you want to give me is its position as a function of time, okay? If you give me this, if you give me theta as a function of time, you're given completely describe the motion. Okay? And that's all I ask of you. Because once I have that, I can calculate the angular velocity and I can calculate the angular acceleration. Okay? And those are the things that I'm generally interested in. Those are two things I'm interested in. Okay? So this is a complete description of motion. Okay? What is this? This equation got messed up. Okay. So theta, okay, when this point moves through a linear distance s, and if this is r distance away from the axis of rotation, theta, the angle in radians, is given by s over r. Okay. And since this is length and that's length, theta is dimensionless, and we give it the artificial unit radians. Okay. So if the radius was 10 meters and you travel 10 meters, then you have covered an angle of 1 radian. Okay. And what is 1 radian equal to in degrees? It's about 60 degrees. Okay. It's a little less than 60 degrees, but all right. So just like for linear motion, when the object moved from initial point to the final point, this was the displacement. Okay. That was the displacement. So when an object rotates from this initial position to that final position, the angular displacement is theta final minus theta initial. Okay. All this should be equal to sign. Redid the slides and it didn't render properly. Okay, I'll fix that and repost them. Okay, so this is the angular displacement, just like this was the angular linear displacement. So the displacement vector is a vector that points from your initial position to your final position. Okay, that's the displacement vector. Average angular speed. Angular speed is angular speed denoted by omega. Okay, average angular speed is angular, okay, displacement divided by the time over which this happened. Okay, and instantaneous angular speed, which is our angular velocity, is d theta by dt. Okay, so this is the parallel of dx by dt. Okay.
The squares are equal signs?
I'm sorry?
The squares are equal signs?
Yeah. I don't know what happened. I just changed slides a few minutes ago, and when I converted it to PDF, it didn't convert properly. All right, so angular velocity is d theta by dt. Now, velocity, what is velocity? Is it a vector quantity or a scalar quantity? Vector quantity, okay? So the question is, what is the direction of the velocity? Okay, and here's the convention. So if something spins like this, here's how you find the velocity. Okay, you use your right hand. Okay, your fingers fold in the direction of the spin, and your thumb points in the direction of the velocity. That's how you find the velocity. Okay. So, and you're using your right hand. Okay. So, what kind of motion are we considering? We're considering a fixed axis motion. So the axis is going to point like that. It's not going to change. So the object can either spin this way or that way. There's only two things it can do. Okay. So looking at from the top, it can go counterclockwise or clockwise. So the velocity can either point in that direction or that direction. Just like for 1D motion, the velocity can either point this way or that way. And we took that as positive and this as negative velocity. The direction was indicated by positive and negative. So just like that, angular velocity, this will be positive and that will be negative, okay? Or one can be positive and the other can be negative. So the velocity, angular velocity, can only point along the axis, and one direction is chosen as positive and the other direction is chosen as negative. All right, so if it's spinning at a constant rate, the angular velocity is constant. When does it accelerate?
Angular velocity changes.
When the angular velocity changes, okay? Now, we're not going to change the direction of the velocity, so all we're going to do is make it go faster or slower, okay? So if it's spinning faster and faster, then the velocity is increasing, so acceleration is pointing in the same direction, okay? Just like in the linear case, in the one-dimensional case, if the velocity is pointing in this direction and acceleration is pointing in that direction, then it's speeding up, okay? So just like that, if acceleration and velocity point in the same direction, that means it's speeding up, okay? And if acceleration points in the opposite direction, then what is happening is this is slowing down, okay? So that's angular velocity, and if angular acceleration is pointing in the same direction, this is speeding up, and here is the case where this is slowing down if angular acceleration is pointing in the opposite direction, okay? So let me show this to you on this wheel, okay? All right. So what is the direction of the angular velocity now? I point my fingers in the direction of the spin, and that's the direction of the angular velocity, okay? What is the direction of the angular velocity? Still that. What was the direction of the acceleration? It's slowing down. It was in the opposite direction, okay, when it was slowing down. What's the direction of the angular velocity? That way. What is the direction of the angular acceleration? Still that way, okay? All right. So velocities and acceleration, all directions are along the axis of rotation, okay, for velocities and acceleration. All right, so now we know how to figure out the directions of the velocity, okay? But most of the time we won't be dealing with it, okay? We won't be using that, okay? Again, so what is angular acceleration? When the angular velocity changes, you have angular acceleration, okay? Angular acceleration is denoted by alpha, and alpha is d omega by dt. Again, these should all be equal signs, and I'll fix that, okay? So instantaneous angular acceleration is d omega by dt, okay? Again, the spin, the rotational motion of this guy, of a rigid object about a fixed axis, can be described by given theta as a function of time. Okay, theta is the angular position of this guy with respect to some reference axis. Okay, so that can be theta. Once you're given that, you can calculate omega, which is d theta by dt, and you can calculate alpha, which is d omega by dt. Okay. All right, so alpha, the angular acceleration, is time rate of change of angular velocity. And you saw that if it's speeding up, angular velocity and angular acceleration point in that direction. And if it's spinning in that direction and slowing down, the angular velocity points in that direction, acceleration points in the opposite direction, okay? So omega and alpha in the same direction, this is speeding up. And if omega is pointing in that direction, alpha, this is slowing down, okay? All right, so the sign convention, if angular velocity and angular acceleration point in the same direction, the object is speeding up, and if the angular velocity is pointing like that, acceleration pointing in this direction, then it's slowing down, okay? All right, so again, using this wheel, okay, so right now the angular velocity is pointing up, acceleration is pointing down, okay? Angular velocity is pointing up, and angular acceleration is pointing up. Okay? Again, remember, we are doing rigid objects about a fixed axis. Anything we are talking, does it apply to this? No. Okay. Why didn't it apply to that? I'm sorry? No, the axis was moving. Right. The object was still rigid. Okay. Yep.
So you're saying velocity points up the axis.
Both velocity and acceleration point along the axis. If it's spinning this way, it points like that. And how do you find that? Using your right hand. You point your fingers in the direction of the spin, and your thumb points in the direction of the velocity. Your fingers point in the direction of the spin, and the thumb points in the direction of your velocity. It's not your left hand. You always use your right hand. Okay? So that's the agreement across the world. We could set up the same rules using your left hand, but everybody would have to be on the same page. Okay? All right. This is something we won't use too much, but let's say this was a wheel and that was rotating. Okay, a point. So this is the axis of rotation. Okay, and what this. So this is the parallel of position vectors. Okay, but again, we won't use this because this only applies for small displacements. Okay, so the position vector of this guy was r, and the parallel of that is here. Okay, so, and when this guy moves from a point moves from here to there, that was the displacement vector. Okay. All right, so here's an object. So I'll draw an object for you guys, and this is spinning. Okay, this point, when the object turns by a little amount, d theta, this point moves that distance, ds. Okay, so this only works for infinitesimal displacements. And d theta would be a vector in this direction cross r. R is the vector of that point from the axis of rotation. Okay. Again, we won't use this. This formula works only for infinitesimal displacement. This is the displacement of that point, which was r away from the axis of rotation, and when the object rotated through this angle d theta. Okay, so it's showing you that displacement, linear displacement, as a cross product. Okay. All right. Similarly, velocity vectors are similarly related. Okay, so if this was an object that was rotating like that, there's the angular velocity of the object, and the linear speed of an object of a point r from the axis of rotation is given by the instantaneous velocity is given by the cross product of angular velocity times how far you are from the axis of rotation. Okay. And again, like you used to say, okay. So on this wheel, so angular velocity is pointing that way. What is the velocity of this point? It's pointing in that direction. Okay? And omega cross r will give you a velocity in that direction. Okay? All right, so let's say, again, here is the disk that is spinning about this axis. Okay, so omega is pointing in this direction. Let's say it spins faster. You make it spin faster and faster. Okay, so angular velocity is increasing. Okay, and what is happening to this point? This point is going with the speed in this direction, and as it spins faster, what is happening to the speed? So again, here's the wheel. As the wheel spins faster, what is happening to the speed of this point? Is it increasing? Right now it's constant, right? when the angular velocity is constant. But when it's spinning faster, the speed of this point is increasing. Okay. And so that point has what is called a tangential acceleration. When the magnitude of the velocity increases, it has a tangential acceleration. Okay, so the rate of change of increase of the speed is called the tangential acceleration, and it's pointing in that direction, is the angular acceleration of this spinning wheel times r, the distance the object is from the axis of rotation. Okay? And alpha is the angular acceleration. So the tangential acceleration of this guy is alpha cross r. Okay. This tells you the rate at which the speed increases. Okay. Again, all these are equal signs, and I'll fix them. Okay. So, well, this is a plus, that's an equal sign. Okay. So omega final equal to omega initial plus alpha times t. Okay, so for one-dimensional linear motion, okay, when the acceleration was constant, okay, the final velocity in terms of the linear velocity was given by, final velocity was linear velocity plus a times t. Okay. The exact parallel in rotational motion is that this is the final angular velocity is equal to initial angular velocity plus alpha angular acceleration times time. Okay. So again, this formula is valid when acceleration is constant. Okay. Just like this was valid when acceleration was constant. Okay. So for constant acceleration, final angular velocity is initial angular velocity plus alpha times t. Okay. Similarly, so for a linear motion, you had x minus x naught equal to v naught t plus 1/2 at squared. The parallel of that is theta final minus theta initial is initial velocity times t plus 1/2 times alpha t squared. Okay, so the exact same formula. Again, this equation was valid when acceleration was constant, so this gave you the linear displacement as a function of time, or you can think of it as position as a function of time. Similarly, this is giving you the angular position as a function of time. Okay. Again, when are these things valid? When acceleration is constant. Okay. Okay, so what these two formulas, so this formula is, this one is omega final square equal to omega initial square plus 2 alpha theta final minus theta initial. And this is the parallel of v final square equal to v initial square plus 2a x final minus x initial. Okay, so this is giving you velocity as a function of position. Okay, final velocity after this displacement. Again, giving you velocity as a function of displacement. This is giving you final angular velocity as a function of displacement. All right, now let me point out an important thing in this thing. Okay, so let's say this guy started here. Okay, so let's say theta initial is 0. Now he spins. Okay, what is theta final? Okay, so this was the x-axis. He started at x equal to 0, and then you spun it. Here's one complete revolution and then second complete revolution. And the line has come back to the x-axis. What is the angular position? What is theta final?
0.
Okay, so it's 760 degrees, okay, or 4 pi, okay? So you have to count all the angles that you've rotated through, Okay, so in these formulas, omega final is the total angle that you've rotated through. Okay. All right, so this formula was that, and this guy is theta final minus theta initial equal to 1/2 omega final plus omega initial times time. So this is the average angular velocity times time. And this guy is the parallel of x phi 1/2 v final plus v initial times time. Okay? 1/2. This is the average velocity times time. All right, so here are the kinematic equations. So these were the equations that you used when acceleration was constant. Again, final velocity as a function of time, final position as a function of time. Okay, position as a function of time. Velocity as a function of position. Okay, so this would be a velocity after you've traveled this distance. Again, valid for acceleration, constant acceleration. And here are the parallel equations for rotational motion. And again, always for constant acceleration. Final angular velocity as a function of time. Final angular position as a function of time. Final angular velocity as a function of displacement. Okay, final position is initial position plus average velocity times time. Okay. So if this angle was 0 degrees and this was 4 pi, so that would be average angular velocity times time. Okay. All right, so in this chapter and next chapter, what you'll see is every equation that you have will have a corresponding equation for angular motion. Okay. And here's the recipe. Okay. So this is for linear motion. And this is for angular motion. Okay, how do you measure the location of the guy? By giving its x coordinate. How do you measure the location of this guy? By giving the angular position. How fast is he moving? Linear velocity, angular velocity. Linear acceleration, angular acceleration. Okay? You will learn in a little bit mass gets replaced by moment of inertia. Okay? You will learn forces get replaced by torques. Okay. Linear momentum gets replaced by angular momentum. Kinetic energy is 1/2 mv square. Okay, can anybody tell me angular kinetic energy, rotational kinetic energy? Omega square, 1/2 I omega square. Okay? Okay, so linear motion, angular motion. What is Newton's second law? F equal to ma. Torque will be equal to I times alpha. Okay. This, remember, was a special case. When is this valid? When is this true? When the mass does not change. So when mass can change, for instance, for rockets, here was the correct form of Newton's second law. Force was equal to rate of change of linear momentum. So similarly, this is valid when moment of inertia does not change. Okay? And you'll see situations where moment of inertia changes. So for instance, when an ice skater is spinning, you'll see that the moment of inertia depends on how the mass is distributed about the axis. So when you fold your arms, the moment of inertia will change. Okay? So for cases where the moment of inertia changes, it'll be dl by dt. Okay? And again, so over 2 chapters, you're learning all this. Everything that you learned for the linear motion, you will learn for angular motion, angular rotation. Okay, And if you replace these variables, you get the corresponding formula. Okay? All right, so, and this is the equations of kinematic motion. These are valid for constant acceleration. Okay? All right, now what we're going to do is the following. So here's a rigid object rotating about this axis, an axis going through this point. So the axis is coming out of the plane of the paper. This object is rotating, okay? And you can see that this point is going in a circle like that, which is going in a smaller circle. The further you are from the axis of rotation, again, the axis of rotation is coming out of the plane of the paper. The further out you are from the axis of rotation, the bigger the circle you have to go in the same time, and so the faster you have to move. Okay? So what we are going to do is relate the speed of this point to how far you're from the axis of rotation. Okay? The angular speed of every point is the same. Okay? So what this gives you is, what this formula is giving you is V equal to R omega. V, the linear speed of this point, is how far you are from the axis of rotation, times angular velocity. Hey guys, leave. I'm asking you to leave. All right. So what we're doing is relating the linear speed of that point to the angular speed of this guy. Okay, V is R times omega. Yep. All right, so if this guy has angular acceleration, okay, this guy will speed up, and the tangential acceleration is given by R alpha. Okay. Tangential acceleration is R times angular acceleration. All right, now let me point out something very important. Okay, so what are these formulas doing? They're relating linear quantities to angular acceleration. So here is linear acceleration to angular acceleration. Okay, and so here's a distance thing. In these formulas, this guy has to be in radians per second squared. So this guy, all the angles have to be in radians. Okay. This guy is in radians per second. So whenever you see a formula that relates linear quantities to angular quantities, that angular quantity is in radians per second square, or whatever. Okay? So for instance, you saw there's theta. This distance S is related to theta like so. And this has to be in radians. Okay? This is in radians per second. And AT, the tangential acceleration, is R alpha. This is in radians per second squared. Okay? So whenever you see a formula that relates linear quantities to angular quantities, that angular quantity is in radians, or radians per second, or radians per second squared. All right, so what this formula is saying is, okay, so we have two formulae here. Yeah. This guy is tangential acceleration is R times alpha. And this is centripetal acceleration is, okay, AC equal to V squared over R equal to R omega squared. All right, so what this is, so here, let's say here's an object, this is rotating about this axis, okay? The axis is coming out of the plane, it's perpendicular to the plane, this guy is spinning like that. Okay, so, and if he's speeding up, then he has angular acceleration. So if he doesn't have angular acceleration, then the speed will be constant. But if he's speeding up, he'll have this point will have tangential acceleration, his speed is increasing. And because the velocities, the direction of the velocity of this guy is changing, he will have centripetal acceleration as well, or radial acceleration. Okay, so this is his tangential acceleration at a given instant. That's how far he is from the axis of rotation times alpha. And this is the centripetal acceleration when his speed is that. Okay, so every point when the object is rotating and has angular acceleration, every point has tangential acceleration and radial acceleration and centripetal acceleration. Okay, so the tangential acceleration is given by that, and centripetal acceleration is given by this. Okay. Centripetal acceleration is v squared by r. Okay. So when do you get radial acceleration? Because the velocities change, linear velocity is changing direction. And you see linear velocity is changing direction because, okay, and tangential acceleration comes about because speed changes. Linear speed changes. It's going like that here, and it's going faster here. Okay? Yep.
So centripetal acceleration and radial acceleration are the same thing?
Yeah. Mm-hmm.
They are, they aren't?
I'm sorry? They are. AR is the same as, okay, so some people like to call it radial because it's pointing in the radial direction. This is centripetal is more specific because it's pointing towards the center. Radial could be pointing outward as well. So this term is, I like that term more. Yep. All right, now what we'll do is we'll define the parallel of mass in rotational motion. The mass gets replaced. The parallel of mass is something called moment of inertia. Okay, and I'm going to quickly go over the slides, but I'm going to point out stuff. Okay, so here's an object that's rotating. Okay, it's rotating about this fixed axis. Okay, this guy, the speed of this guy is that. The speed of that guy is that. Okay, so what we'll do is, here's this object. We'll break it up into little pieces. A million little pieces. What is the kinetic energy of this guy? The kinetic energy of this guy plus the kinetic energy of this guy plus the kinetic energy of this guy plus the kinetic energy of that. The kinetic energy of each piece is that. So the total kinetic energy is the kinetic energy of each piece, and then you sum over all the pieces. The problem is each piece is going at different speeds. But what we can do is we can be smart about it, and we can write this as Ri omega. The angular velocity is the same for each piece. Okay, so we'll do that. You put that in here, Ri omega square, and omega is the same for each piece, and that can come out. Okay, and so the kinetic energy, what this formula is saying is 1/2 summation over I mi Ri square omega square. What is this piece? This piece is the mass of this piece times how far you are from that piece squared. And you sum over all the pieces. And this guy we call the moment of inertia. So in rotational motion, m gets replaced by I. Okay? So the kinetic energy is 1/2 I omega squared. Okay. Now let's look at the moment of inertia. The moment of inertia, well, the moment of inertia depends on the mass of these pieces and how far is the mass from the axis of rotation. Okay, so what you can do is you can take the same wheel and make the spokes longer. You haven't changed the mass, but you have increased the moment of inertia. Okay, so take the same wheel, you increase the spoke length, the moment of inertia increases, and it turns out that it'll be harder to rotate give the wheel the same angular acceleration. Okay? So the same object can have different moments of inertia. So I have only one mass. But if I'm rotating, like let's say I'm a skater, I'm rotating about this axis, now my moment of inertia is greater. Now it's smaller, smaller, smaller. How many moments of inertia do I have? Infinite. Okay? So an object can have infinite moments of inertia, okay, but the same mass. Okay. So the kinetic energy is 1/2 I omega square, and this is the parallel of 1/2 mv square. Okay? You guys understand? Okay. So how many moments of inertia can an object have? Infinite. Okay. It depends on what axis you're calculating the moment of inertia about, and so on. So we'll illustrate that for this object. So here's this object. If you calculate the moment of inertia about this point, this axis, okay. So moment of inertia is each mass times the distance from the axis of rotation squared. So if you calculate the moment of inertia of this object about this axis, these two guys do not contribute because r is 0 for them. Only these two objects contribute. And the moment of inertia is I equal to 2ma squared. Okay? This mass, only these two guys contribute. The same object, if you calculate the moment of inertia about this object, now all the objects are contributing. And the moment of inertia is 2ma squared plus 2mb squared. Okay, so it increased by that much. Okay? And again, this is just 2. If you calculate the moment of inertia of this object by this about this point, that'll increase even more. Okay? So moment of inertia, again, like I said, is for any object, you can have infinite values. Most of the time, we'll be interested in the moment of inertia of an object about an axis passing through the center of mass. Okay? All right, moment of inertia is an extremely important quantity, and so for uniform objects, you have tables like this. Okay, so moment of inertia of a hoop for an axis passing through the center, for that axis, for that axis, for that axis, for this axis, moment of inertia of a uniform rod about that axis, and so on. Okay, yep.
Are we gonna have a table like that for the test?
I'm sorry?
Are we gonna have a table like that for the test, or are we gonna have to?
Yeah. You'll have a table like that for the rest of your life. You don't have to remember anything. Okay. All right. So moment of inertia are extremely important quantities. Okay. So if you wanted to calculate the moment of inertia, this would be the density r squared dv. You would do a triple integral for a solid object like this, and you'll do problems like this in your Calc 3 classes. Okay. So, and somebody's done the triple integral for you in this case. So for an object with uniform density, the moment of inertia about an axis passing through the center of mass is 1/2 times the mass times r squared. Okay? R is the radius of the cylinder. Again, this formula works only for a uniform cylinder. If the cylinder was not uniform, it wouldn't work. Okay? And again, like I said, this is an important enough stuff where you have tables for all kinds of things. You know. Now, of course, in this table, Generally, they give you a moment of inertia about the center of, about an axis that passes through a center of mass. Okay? What if you wanted to find the moment of inertia about this axis, for instance? In a table, all they'll give you is moment of inertia about an axis that passes through the center of mass. Okay? And so then you use a parallel axis theorem. Okay, so if in a table you can look up the moment of inertia about that axis, and if you want the moment of inertia about an axis parallel to an axis passing through the center of mass, the moment of inertia about this axis is the moment of inertia about this axis, which is given in a table, okay, times the mass of this object times d squared, plus mass times d squared, okay? So you can find, if you know the moment of inertia about this axis, now you can find the moment of inertia about any axis parallel to that axis. Okay? So the parallel axis theorem, if you know the moment of inertia about one axis, you can calculate the moment of inertia about any axis parallel to that axis. Okay? All right. I guess I got too many slides, so we'll stop here and